Okay, and so for this last pre-recorded lecture, we're going to talk about climate change and how the ocean factors into that climate change, and hopefully make some linkages across the topics from what we've been talking about in ocean circulation and budgets, thermal balances, all that, freshwater balances, all that, and touch back onto how this kind of thinking gets applied in modern climate change science, with an eye towards modeling the Earth specifically, not so much other planets. The Earth has a big ocean, etc. But some of these ideas you could even bring on into other planets as well. When I took this course, folks were not terribly interested in talking about climate change as an aspect of dynamics, not this course, but the equivalent course, although there was starting to be a sense of that. And one of the reasons is that everyone thought that it was an overly politicized field and that it wasn't really getting into the deep nitty gritty of the science or something like that. I don't know. It was some kind of series of things where it was like, oh, if we set up our problems cleanly, we'll be able to talk about the things that we can solve more than whatever. But I think over recent years, we've come to realize that this is just a problem that we need to work on, a problem that we need to think about, and a problem that we need to do the best that we can, given the constraints of the problem at hand. And so rather than burying our heads in the sand, we might look the ostrich right in the eye and think about what is going on. What are the issues behind climate change? What are the ocean topics that can be applied? How do we think about it? How do we get the pieces right or wrong? Okay, so I'm going to mainly draw on stuff from the AR5, the fifth assessment report from 2013. A lot of this is reproduced in the with and updated in a report since that. But this is one that has all the topics together. So most of these figures are going to come from that report. Let's see. So here, this is a budget of the Earth's energy. So on the left is the different forcings to energy. So well-mixed greenhouse gases are this kind of purple range up here. The total energy budget is here. Short-lived greenhouse gases are down here. That's things like methane. Solar changes in the solar cycle over the span of years. This is relatively small, including zero piece. Land use change actually is a negative number according to this estimate. Volcanoes is a negative number because the aerosol, the small particles released from volcanoes block sunlight. And then this final one of the tropospheric aerosols, those are the regular kind of soot aerosols that particulate emissions and also naturally occurring particulates that also blocks the sun. So you put all this together and you get this black line, which is showing that we expect to be warming. The cumulative energy over this time window from 1970 to 2010 is in the ballpark of about 800 10 to the 21 joules, zettajoules, 800 zettajoules. Okay, where is the energy in the world? Well, most of it is stored in so this is the storage. Well, it's broken up into a storage part, which is the warming of the Earth system, which is over 90% in the ocean. That's about 200 zettajoules. And then the radiative responses under different assumptions about the way that the Earth responds to warming are given here. But the point is that most of the main thing that changes is the energy outflow responds to this change in energy inflow, and then only a little bit is left over to be stored. But that little bit that's left over to be stored is still a substantial bit left over to be stored. There is a lot of people talking about, well, CO2 isn't toxic, so what's the problem? It's not a pollutant. Pollutants are toxic. It is a toxic pollutant. If you inhale air that's got 385 parts per million carbon dioxide and you exhale it with about 10 times as much, and that extra carbon comes from what you eat. So this is absolute nonsense. So this is one of the logics that people use. But the definition of a pollutant is actually anything that can lead to adverse effects in the environment in sufficient concentrations. It doesn't matter whether it's naturally occurring. It doesn't matter whether it's causing toxicity or whether it's just having other deleterious effects. And so CO2 falls into the category of something that has other deleterious effects. And we are at far below the toxicity level, but far above the level where the Earth system can reabsorb the emitted CO2 and prevent it from accelerating greenhouse warming of the planet. And where does all that carbon dioxide come from? Primarily, it comes from fossil fuels. So when we think about the carbon cycle, we have things like trees are taking up carbon and cows are eating the trees or eating the grass and then emitting methane and or decaying or being eaten and then breathed out as carbon dioxide back through us. But the point here is that all of these things are not yes or no questions. You could say, oh, this is a negligible part of the overall carbon budget of the Earth without humans or with humans, or fossil fuels don't matter that much. The point is that all of this stuff is not a yes or no question. It is a how much question. It requires a quantitative appreciation for the way that the system works. So what we've been talking about all along this semester, talking about quantitative changes to ocean circulation, quantitative changes to budgets, that's exactly the same tools that you use to approach the climate problem. And so when you try and draw up what a carbon budget of the Earth looks like, this is again from the 2013 IPCC report, you get these black numbers as the natural situation, and then the red numbers are the anthropogenic perturbation, and these are reservoirs in the boxes, and then there are fluxes between the reservoirs and the arrows. And the first thing you should notice is that the reservoirs are much bigger than the perturbations, which you can think of it a lot of different ways. So the surface ocean's got a lot more carbon in it than the anthropogenic perturbation does. The intermediate and deep ocean have a whole lot more carbon than the perturbation does. Doesn't mean that it doesn't have an impact. This is true also of the fluxes, that the flux back and forth between the air and sea is much, much larger than the flux from air to sea of the perturbed fluxes, and way larger than the imbalance, which is about only a tenth of that. Maybe on the other side of the story, we haven't burned even a tenth of the fossil fuels that are estimated according to this budget. So that's a pretty massive change. And the land use changes are also pretty small. The atmosphere, however, notice that these numbers are not equal in all the different components. The atmosphere has grown by a pretty substantial hunk. It's grown by over a sixth. And so what does that tell you? It tells you that the atmospheric budget is a variable part of this whole system. The storage is not typically in the atmosphere. The storage is in these other components, and the fluxes are making those exchanges. So now the question becomes, if you put something into the atmosphere from burning some fossil fuels, are these fluxes going to readjust in such a way that the oceans take it back up, or the soil, or the land? That's the key question. So it is, again, a quantitative question. How resilient is the system to the emitted amount of carbon dioxide? So how could you figure this out simply? Well, you could just go and measure the carbon dioxide levels in the atmosphere and see what you get. Bingo. That's what Keeling has been done. And this is an update. This is not updated by this. I just updated by downloading it from Scripps again. So I'll delete that. So this is the so-called Keeling curve. This shows the parts per million concentration of, so if it were 1,000 parts per million, it'd be 1 part per 1,000. So 0.3 parts per 1,000. That's the carbon dioxide concentration as measured on a mountaintop in Hawaii, which is very clear, undisturbed air, the direction that it's coming from. And so up it goes and up it goes and up and goes. There's a seasonal cycle, which is very interesting to think about. Why there would be a seasonal cycle in carbon dioxide has to do with the breathing of the Earth system, of the biosphere. And then there's a background mean upward trend. And if anything, the trend is just accelerating. So this is as long as we have been measuring this from 1960 to present. We actually have now since this curve, we have gone back and analyzed gas bubbles and ice cores and other things to get better context from this. We'll come back to that in a little bit. If you try and make the same kind of measurement in the ocean, you can measure the pH of the ocean or the partial pressure of CO2 in terms of atmospheric units in the ocean, surface ocean CO2. And you can see that that's also going up. And these units are such that you can compare essentially these numbers to these numbers and see that the ocean is ballpark the same, lagging a little bit behind in the air-sea flux exchange. And then the pH is going down and down. pH going down means acidic, ocean acidification, because of increasing carbonic acid, dissolved CO2, and then its byproducts. I just pulled this number down a little while ago, but actually we crossed 420 for the first time just in the past couple of days. So this is even out of date now. This is a big number. A lot of people are measure what their date of their birth was. So I will say I was down in the low 330s when I was born, and we are at 420 now. Okay. So dilution is the solution to pollution. This is one of the key ideas behind waste disposal. But a pollutant, as we said, it's any substance present in the environment in harmful concentration, which adversely alters the environment. It doesn't have to be toxic, it just has to have an adverse effect on the environment, and it has to be at a harmful concentration. So we could dilute it, which reduces the concentration, or we could capture it and concentrate it, but then leave the environmental part behind at a level that's low enough that it's not harmful. Those are the kind of solutions that you think about when you think about or you could avoid releasing it in the first place. Those are the kind of thinking that you could think about when you think about a pollutant. This is a qualitative, you might have a distinction between a qualitative pollutant and a quantitative pollutant. A qualitative pollutant is something that you worry about in the environment. Maybe there's not enough of it to cause an impact. But CO2 is a good example of a quantitative pollutant. Its effects are totally negligible, in fact, beneficial. That's what plants breathe in small amounts, in the natural amounts, but in excess quantity, it starts to trigger adverse effects on the environment. So again, we're coming back to the notion that quantitative understanding is key to understanding climate change. All right, so let's see, where does the carbon come from? The figure is from the Global Carbon Budget from 2020 update, which just came out a couple months ago. So this is the global CO2 emissions. So now we're not looking at the CO2 concentration in the atmosphere. This is the sum of the emissions. Here are the emissions in gigatons per year. Broken down by country or block of countries in the EU case. So you can see the EU and the US have started to decrease. India has started to increase. China underwent a huge increase and then has leveled off in recent years. Hopefully all these will start going back down, but we don't get to not worry about climate change until all of these sum up to zero. Right now, we have seen no sign in fact, including the pandemic year, that this is going down. It still continues to go up. So what about what fossil fuels are behind this? And so you can look at some of the similarities between this and this in terms of the shape of these and get an idea about what the fossil fuel burning of each different country is, because clearly coal is the only one that's going down. Oil and gas and cement are all going up. So if there's any going down, it means transitioning from coal into something else or using less of one of the others, country by country. That is this part of the story. And these are in CO2 emissions, gigatons per year of CO2. So this does not tell you how much energy you get out of each of these sources for the same amount of CO2. So you could make a different metric of this, which was talking about the energy production based by each of these. This is not the energy production, remember. This is the carbon dioxide production. So you gaining efficiency by switching to a more efficient source doesn't really work out here, because this is not balancing the total energy. This is just counting the total pollutants. And then if we do the maybe more damning of the United States case, and we divide these numbers by the population of those countries, you see that the United States is by far the largest per capita emission. So that's per person. Continues to be big. China has just made a surge and has just reached up about the EU levels. The EU and China, however, are less than half of what the typical American is. India is much lower. Global is lower, is somewhere below the EU and China right now. So what this says is that it's not only the fact that these are big countries with big economies. The USA is leading because the lifestyle of an American is different than the lifestyle of someone in the EU, someone in China, someone in India. Okay, where does it all go? Well, the carbon is getting absorbed, or it just stays in the atmosphere. So here's an inverse budget of trying to figure out where it goes. So here are the sources in gray for the fossil sources, and here's land use change in this sort of orange color. That's what we have to get rid of, and then the bottom is where it goes. So ocean is green, land is light green, atmosphere, that's the part that's leading to this parts per million increase, is the blue. And for a little while here, we weren't sure what was happening because it didn't add up. Probably means that we missed counting some of them, but most of the time, the leading edge of this tracks pretty closely along this, which is just the mirror image of this. That's the source. And so the sinks balance the source. This is another way of looking at the country by country breakdown. This is essentially this upper curve, the emitted, broken down by country. And so you can see the United States this is sort of more or less the same. The EU and developed, and the United States is this whole blue wedge. Then here's the Russia, which is decreasing actually, China, which is increasing, India, which is increasing, and the rest of the world, which is also increasing. You add this all together, you're getting up into the 30 billion metric tons territory in recent years. Okay, so why do we care about this? This is not, this is gigatons per year. This is not gigatons per year. This is total cumulative emissions. And why do we care? Oh, no, it is not. This is still gigatons per year. We actually want cumulative emissions. That's because the temperature, the response of the system and warming level is not a response to today's emissions. It's actually a response to the CO2 levels and the energy budget. It goes through all these permutations. It turns out what it's closest to is that temperature is proportional to the cumulative emissions. Let me show you what I mean by that. This is showing a bunch of different scenarios and observations of all of the different future possibilities from different scenarios, lower warming levels, faster warming levels, and sorry that this is blurry. I should have cut and pasted this one again. And here along this axis is the amount of anthropogenic CO2 emissions since 1870, so 1,000, 2,000, 3,000 of the gigatons carbon dioxide. And then in this direction is the temperature anomaly relative to that early time, 1861 to 1880. And you can see that there's pretty much a linear relationship between all of these pieces. So there is just a relationship between cumulative anthropogenic CO2 versus the temperature anomaly. That is a very special kind of relationship, and it implies a lot of things about how capable the sinks are of removing the CO2 from the atmosphere, how the CO2 affects the energy budget, which then affects the temperature. A lot of complexity in there, but the simple thing is the practical aspect of this problem is that you don't have to think hard about how much warming you get for a certain amount of emissions. They are proportional to each other. So it doesn't matter whether we cut our emissions this year or next year, all of the emissions we're doing in those 2 years combined add up to be more warming. And if we go to net zero today, it doesn't make us guilt-free because we have all those years that we used to be emitting that are still in the system. That's still part of the warming that's coming. And if we emit quickly, we will get to these high temperatures fast. If we emit slowly, we're still on the same pathway. We just don't get as far along the path as fast. So these dates are the years by which we reach different points. So in a nutshell, the Earth's capable of absorbing some excess CO2 through land, life, ocean, rocks. It's the rate of emission that's the problem. Burning fossil fuels globally means taking millions of years worth of buried fossils and putting them in the atmosphere fast. And that's when we get to this linear response of the system. Okay, so global warming isn't just a carbon problem, though. Carbon toxicity isn't the problem, with the exception of ocean acidification, which actually is carbon toxicity. The acidification due to the excess carbon kills things, but it's more that the carbon dioxide affects the energy on Earth. And now, is energy a pollutant? That's an excellent question. Think back to what we just talked about with qualitative versus quantitative pollutants. How much energy should we have? How much energy what does it mean for energy to become toxic? What does that mean? Great. Okay, so now if we're thinking about energy budgets, we can go back to our little energy budget that we've talked about a bunch with the incoming solar and the reflected, the outgoing long wave, the CO2 in the atmosphere that changes the outgoing window, warming up the mixed layer, all that stuff. And as we said last time, about 90% of the anomalous warming is in the oceans. And so that's warming of the oceans is also the part that goes to sea level rise, but now we're starting to think about it in terms of the energy. 0.7 watts per meter squared to the atmosphere is only about 1.5 Kelvin per year. So these numbers are helping us get a handle on how much warming there could be from a 0.7 watts per meter squared, for example. How much is going into the oceans, what the watts per meter squared are over the whole globe on this side, and then the different sinks of this excess energy. And so the energy goes into the ocean. We talked about it this way. This is in terms of energy, but it also, we could put this in terms of thermospheric sea level. So the term of art is ocean heat content, which is the energy that goes into the ocean. And that ocean heat content is relative. There's no overall meaning to it. You pick a particular date and then you look at anomalies versus that. So you can think of it layer by layer, top to bottom, or you can think of it basin by basin. These are the different breakdowns here. Either of these is a reasonable way of thinking about where the ocean goes. So let's see, what are the big signals here? Well, you can see the Southern Ocean has got a huge fraction of this. That's really important. And then if you look at the North Atlantic, it's got a relatively small fraction on this side. Tropical, subtropical Atlantic, it's got a pretty big part. Now, whether this heat came in through the surface into the tropical, subtropical Atlantic, or through North Atlantic deep water and then brought down, is not apparent from the way this is analyzed. So we imagine the cooling and heating being perturbed at the surface and then following these pathways, all of the oceanographic pathways that we've discussed, and that anomaly in heating, of course, may lead to changes in the baroclinicity of the ocean, but if the changes are modest, which they sort of are, then we would expect that kind of to be a passive tracer marking the pathways of these different water masses as they're subducted down. There's a lot of variability in the ocean, though. So if you go and look, just measure temperature variability at different places in the ocean, on short time scales, most of that temperature variability actually is just to do with the redistribution of heat from place to place in the ocean that's always ongoing. So it's eddies, El Nino, and variability in currents. It's not actually the climate change signal until you have looked over a very long time window, at which point the added heat at the surface through these perturbed surface fluxes starts to become the dominant anomaly that you find. That's concept is called the time of emergence. It's when the global warming signal emerges from the background noise. So this is what global climate models are really built to do. They were built originally to do a bunch of things, but now this is primarily what they're used for. It's a collection of relationships and budgets, just like we've been talking about. Budgets in the atmosphere, budgets in the ocean, budgets on the land, and nonlinear PDEs, just like we've been talking about, are the things that get solved. And this, again, requires a quantitative appreciation of what's going on in the system. Okay, so you take all those, what's going on in the Earth? There are a couple of key statements that you probably should know, even if you're, even if this is sort of an interesting, this is only part of what the things you're interested in. So warming of the climate system is unequivocal. And since the 1950s, many of the observed changes are unprecedented over decades to millennia. So that's the statement about observations. Each of the last 3 decades has been successfully warmer at the Earth's surface than any preceding decade since 1850. So that means there's consistency in the rising on the decadal time scale. In the Northern Hemisphere, 1983 to 2012 was likely the warmest 30-year period in the last 1,400 years. That's a long time. It's not clear which is the limiting wind, like whether they had the record couldn't go back farther or whether this is really warm. Anyway, that's a hell of a statement to say. Ocean warming dominates the increase in energy stored in the climate system, accounting for more than 90%. Great. It's virtually certain that the upper ocean warmed from 71 to 2010, and it's likely warm between the 1870s and 1971. So these are the pieces of this budget that we're pulling together. Over the last 2 decades, the Greenland and Antarctic ice sheets have been losing mass. That's related to the sea level story. Glaciers have continued to shrink almost worldwide, also related to the sea level story. And Arctic sea ice and Northern Hemisphere spring snow cover continue to decrease in set. Snow cover has a sea level impact. Sea ice does not have a sea level impact, but it surely has an air-sea energy exchange impact, which is part of this story as well. So why do we want climate models? One of the main reasons we want climate models is so that we can compare what would have happened if there were no anthropogenic impact. That's something called detection and attribution of anthropogenic effects. What do I mean by that? There isn't really a planet B, but with a climate model, we can get a planet B and use that as a control simulation for what we've done over the last 150 plus years. Here's an example. So this is spaghetti diagram is showing all of the models. The blue line is the mean of all of the models, and the black line is the observations. And you can see that the observations fit within this model ensemble as if one of these spaghetti lines were the observed reality of the Earth, although in fact, none of them were. Each of these differ in weather and El Nino and that kind of thing. You can see in this multi-model ensemble the clear impacts of these volcanic eruptions, even though you may not be able to see it in the observed records quite so obviously. There's a signal to noise problem with all this background variability, and then also imposed on it the volcanic changes. Now, natural forcings, if we remove the human impacts, the greenhouse gases, the anthropogenic aerosols, anthropogenic land change, we get a signal like this. So now the models do not contain the observations. They're quite a bit lower. And in fact, there's not really a trend over this window of time. So over the 20th century, there's pretty much no trend without the anthropogenic impacts, and it's inconsistent with the observations. If you include the anthropogenic impact, it is a substantial trend, over 0.5 degree, and it is consistent with the observations, plus uncertainty. In fact, you can go more detailed than this and break it down in ocean by ocean, continent by continent, and this is basically the same thing, showing the observations in black, the human-induced climate model ensemble in pink, and the natural-only forcings in blue. And you can see in all of the continents, the land actually has, except for Antarctica, the land has separated so that you can tell that the human-induced warming is detectable. So there is a signal where there's no overlap in the error bars. the observations fit within the human-induced profile and not within the other one. In the oceans, there's still a lot of overlap between the two scenarios, but still the observations may have drifted out of the natural forest engulling case and be only in the human, including human case. This is the global land surface, this is land and ocean surface, and this is just the ocean heat content story. So how awesome are climate models? They include everything we know about everything. Any one of these systems is enormously complicated. Using supercomputers, we do it. All models are wrong. Some models are useful. Climate models are definitely no question wrong in lots of details. But in the big picture sense, and the fact that they have a focus on getting this energy budget, these anomalies, or at least an ensemble of models can give you a sense of the scatter of anomalies about that forced signal. They're a great tool, and you just have to think about how to use them carefully. Here's an example, as we saw, of observations of the surface currents, and here's an example of an ocean model which has surface currents simulated. I won't go into the details about how accurate these comparisons are. In a qualitative sense, you can say that they're doing the similar kind of things, which is just super cool, especially all these eddies, which even when I was in grad school, it was not something that we could really simulate directly. So how do we know if the models are doing the right thing? Well, we can form them into a historical model simulation and then compare them to the observations. So here is the multi-model mean surface temperature over 1980 to 2005. And here is the mean bias. That's the offset of this multi-model mean surface temperature versus the observed temperature. And you can see some places are too cold and some places are too warm. That's what you'd expect. The multi-model mean of absolute error. So this is now how many degrees wrong are you between those two. And this is the absolute error. So it's not the average, the way that the bias is. This is the root mean square, but it's not the root mean square, it's the absolute error. So this is gives you a sense of how wrong they are. And then here's the mean reanalysis inconsistency. So this is basically a comparison between weather forecasts and climate models. And then, so that's the game. Okay, so now, all right, we have the concept we want to have these planets be. We have a sense that we want to debug these models, or at least think about how they work and figure out whether we can assess how bad they are, how good they are. How do we figure out how to do it? Well, we do something called a scenario, a set of scenarios, or sometimes it's called a MIP, a model under comparison program. This is for the AR5, the set of simulations that were required over here. And then on the right-hand side is the set of simulations that could possibly be undertaken. So this is each one of these is a different experiment. And in fact, even within these different experiments, there might be multiple ensemble members in some of them, so as to handle that average variability. This is a huge amount of computing. So another thing that we could look into, aside from looking toward the future with computer models and trying to compare computer models versus the observed record, is we can go into the deeper past and look at paleoclimate changes. So paleoclimate changes are as old as the Earth. You know, they go all the way back 4 billion years, and they're broken down into these funny names. These funny names have to do primarily with changes in the fossil record or changes in the rock record that are detectable. A lot of those have now been associated with climate change events, whether they were forced by an asteroid collision or forced by slow changes in the carbon budget or forced by the oxygen breathers. All these kind of things help define this long time series. The most interesting ones are maybe the most recent, or the warmest in the recent past. So the Eocene is a recent warm epoch that people talk a lot about. The Holocene is, of course, the period that some people would say is our present Some people would say we've now switched into an Anthropocene. Either way, Holocene is the recent past, the last few thousands of years. And during the Miocene, the Eocene, the Pliocene, the Holocene, there are relatively warm periods that we might think about as we compare ourselves to and during the Pleistocene, that is the time of glaciations and interglacials. The interglacials are all, somewhat comparable to the Holocene. Okay. Some of the things you might get interested in when you think about the paleo history of the Earth is the fact that we know enough about solar dynamics to know that the sun used to be a lot fainter. So how was the Earth warm when the sun was faint? And so if you work out how much weaker the Earth how much weaker the sun should have been, you get a curve like this that would suggest how much colder the Earth should have been. And then you have to correct for this with a greenhouse effect in order to get us up to where the observed surface temperatures actually were. So the greenhouse effect must have been changing in time in an interesting way. So the point is that the greenhouse effect, the albedo, not only are they important today, but they have been changing and important in different ways in the past, which is an interesting kind of thing that you need to bring all this fundamental physics of how the Earth system works into the way that we understand how it might change in the future when conditions get quite far away from where they are now. And so, like I said, the ice house is when we start having glaciations. Before that, we didn't have glaciations. So we can look back to these warm epochs and talk about things like how high was sea level when there were no, the ice sheets had retracted as much as they were going to, or how much does sea level vary between glacials and interglacials? That kind of question is something that's very hard to get a handle on without looking into the paleo record. Isotopes, something that a lot of people at Brown work on, so isotopes are chemically identical to each other. So the heavy oxygen and light oxygen isotopes just differ by the number of neutrons. So they have the same chemistry, but there are some processes that separate preferentially for heavy or preferentially for light. Those processes are called fractionation processes. So things like evaporation tends to take the light ones, and things like crystallization tends to take, let's stick to evaporation, which is closer to what goes on. So the point here is that if you are evaporating the light one and then it snows down on the ice sheets are going to tend to have lighter isotopes than the ocean. And then if the ice sheets melt, you will change the isotopic balance in the ocean. And so you can effectively measure by watching the isotopic changes in the ocean, you could see how much the ice sheets were changing. Alternatively, you could look at the isotopes in the ice sheets, but that's not what we're thinking about right now. Well, how do you find out what the isotopes were in the ocean? Well, you go back and you look at dead plankton that are in the sediments, and those have a record of the kind of both the Delo-18 that is in the ocean, but also they preferentially take, when conditions are cold, the heavier isotope. So you have two effects to get to. There's how much, what's the background concentration is, and then what temperature they lived at. There's also sometimes a temperature and salinity correction that you have to think about. But this is the kind of tool you can use multiple isotopes at once. You can use multiple isotopes in different kinds of rock records, sediment records. All of this can be put together to get information about what was going on in the past. And it's fairly well preserved because since there's chemical and things are chemically identical, between the different isotopes, you don't have a problem where there's a slow reaction removing one into the other, unless they're radioactive. So you can, if you track the Delo-18 record, you can see Ice ages, so this is millions of years ago, so this is oldest. So here we go down, and then we start getting these ice ages, and then the ice ages change their period in the recent past. All of this is in that Dello 18 record, if you know how to read it. One of the things that we think has to do with why these ice sheets were growing and decreasing is that the orbit of the Earth changes on in a couple of different ways. So the Earth's orbit about the sun is elliptical. There's the perihelion, there's the aphelion, and that relationship between the perihelion, the aphelion, and summer and winter, that is between the tilt of the Earth and where you are in this elliptical orbit, varies over time. So the eccentricity changes, it gets more and less eccentric. So the major axis and minor axis grow and shrink over time. The location of the perihelion versus the solstice changes over time, and so on. So if you take precession, which is that change in the perihelion, aphelion, obliquity, which is the change in the tilt, and eccentricity, which is the change in the major axis versus the minor axis, you can break down the signal of how the sun's effect should be changing season by season, and then see what that looks like. Alternatively, you could take that Dello 18 record and you could break it down by Fourier series into those same bands, and you could compare. When you do this, you see that there is some power, at least in all of these bands in the Dello 18 record, much less power up here in the solar and the insolation record, at least this particular insolation at 65 north in June. And so you might say, hey, eccentricity, this is something weird that eccentricity is excited, but this guy and this guy, maybe maybe their peaks are aligned, maybe you can make some kind of story about how this forcing relates to this response in an interesting way. These timescales are so long, 100,000 years, 41,000 years, 19,000 years, that it's extremely rare for climate models to be run for those full intervals for enough periods to be able to see what the mechanisms underlying these connections are. So sometimes sort of toy climate models, accelerated climate models are used to do this. The extent to which they represent the necessary processes as well is debatable, I guess. All right. So now we have a paleo record, and we have a past projections, and we have an observations. So we can start making the kinds of connections between those things, like saying there's very high confidence in the maximum global mean sea level during the last interglacial period. We know that from the Dello 18 record when it was for several thousand years, at least 5 meters higher than present, and high confidence that it did not exceed 10 meters above present. So 5 to 10 meters above present is about what you're going to get in a typical interglacial. That's a useful number for context for the kinds of multi-meter rises that we are projecting. New results from high-resolution coral records show that the El Nino oscillation was highly variable through the past 7,000 years, showing no discernible evidence for an orbital modulation of ENSO. And so it's not going to change, at least based on this record, as the climate system changes, at least not to the extent that the climate system has changed over the past 7,000 years. Increase in the strength of the observed summer annular mode since 1950 has been anomalous in the context of the past 400 years. So here's now and ENSO doesn't change, but the southern annular mode has changed. That's another kind of contextual problem. 400 years is not something that you can get from the instrumental record, something you can get from the paleo record. And then you could ask whether there's another ice age coming, and it's virtually certain that orbital forcing will be unable to trigger the widespread glaciation for the next 1,000 years. This is partly because of the orbital forcing changes that are coming. We can predict that astronomically, but also because we think that we have higher CO2 levels, and so you can't, even whatever orbital forcings are coming, they're not enough to overcome that. So we can't even forecast the weather 2 weeks ahead. How can we project the climate a century ahead? Well, the idea is that a projection is not the same as a forecast. A forecast depends on the initial conditions, and those become chaotic in short time, and then just like the butterfly effect, and then they lose the ability to be distinguishable after a few predictability timescales is what it's called. But projections, the envelope containing the possible forecasts, is still predictable even beyond the forecast predictability timescale. So climate science is what is involved in predicting the envelope of possibilities. Weather is what's involved in predicting the forecast, the short-term forecast, where the initial conditions are still important. Weather forecasts are getting better and better. So the 1 day forecast error is going down, the 6 day forecast error is going down. This is an amazing treat, but we are still only predicting a few days ahead. And so when we think about this intrinsic problem of air-sea fluxes and weather and turbulence in the atmosphere and turbulence in the ocean, predicting which eddy or which storm is going to be where on which day is definitely not possible beyond the predictability window. But getting some of the sense of the average statistics, the range of possibilities, an ensemble forecast, averaging over all of the weather conditions is what the story is when we do climate change work. And so here we are averaging over the atmosphere in some kind of stochastic sense and seeing a turbulent ocean. It doesn't help you much. So we need to have lots and lots of possible model A's. That's what this whole spaghetti diagram is. They're each differing in weather. They're not differing in climate. The real Earth, the observational record, of course, also disagree. It varies by weather, but we don't have any context for distinguishing weather from climate in that system in an obvious way. By comparison to this ensemble of climate models, we can do it. I'm going to skip a little bit about this. So this is a breakdown of how the different forcing agents sum up to make the total observed change. But here's one related issue about this uncertainty. We can break down the uncertainty in a projection. So here's the total scenario spread over all of the possibilities. Here's the spread within one particular model, the blue one. And here's the orange, which is the level of internal variability that we might expect from that, from deviations in initial conditions. So in the beginning, in the short-term forecast, the internal variability is the dominant thing. We have not yet seen any emergence from that. But over time, the model spread starts to get bigger, which means that we are measuring the model uncertainty, and that's this big. But still the scenario spread, that is what humans choose to do, is bigger still. So in sequence, we are first dominated by uncertainty due to internal variability. Then we are dominated by uncertainty due to model physics. Then we eventually end up with being dominated by uncertainty about human choices. This is kind of fundamental to the way that almost all of the variables work out if you look at them. So here's some of the most important variables. pH is going down. It goes down more in stronger scenarios than in weaker ones. Global average surface temperature is going up. It goes up more in stronger emission scenarios than in weaker ones. Sea level rise is going up. It goes up more in stronger emission scenarios than in weaker ones. Unlike surface temperature at the 2100, sea level is still going up even in the low emission scenarios. That's an important point. And I put ocean heat content on here as well, but it doesn't have scenarios. We did the breakdown by country and by fuel type. You actually can do the breakdown by corporation once you're in the fossil fuel business. And so this is the breakdown of how big, with the size of the bubble being how big each of these producers is. And that's an interesting thing to think about. All right, so it wouldn't be a talk about climate change if we didn't talk a little bit about disinformation and denial. climate skeptics are people who are skeptical that the whole system works out as cleanly as it might. I think of that as a relatively important part of the scientific process, is to get over your skepticism about all of these conclusions being drawn. And in fact, the whole IPCC process, all of the science I just showed you was largely in response to kind of the doubting crew of the skeptics. Well, is it cumulative emissions that count, or is it annual emissions that count? Is there enough? How long does it take for the climate change to emerge from the background of internal variability? How uncertain are the models? How much model spread is there versus how much scenario spread versus how much internal variability spread? Those kind of questions required a lot of focus and attention to get precise on. And it's that precise question that gives you actionable information as opposed to just hunches about how things should work. The second part, a climate denier, is someone who, even confronted with this evidence, sort of refuses to change their mind in response to it. There are lots of preconceived notions. People have lots of, the Orwell quote is that one of the hardest things to do is to get someone to convince something of a fact when their job depends on them not being convinced of it. That's an interesting human factor. That's another piece of it. Disinformation is actually a separate, more difficult aspect of this whole problem. And we are only now starting to learn the scope of to which disinformation has been used. So disinformation is different from misinformation. Misinformation is just being uninformed or misinformed, uninformed or misinformed. Disinformation is information, or something like information, that is used to actively flood the zone or confuse the audience and make it seem as if there's less understanding than there is. So here's an example of the level of penetration of information and misinformation. Do you think human activity is a significant contributing factor in changing mean global temperatures? The general public is, at least at the time of this survey, was at around 55% in belief. People who were scientists but not publishers and not climatologists are here. Here are climatologists. Here are active publishers of all topics. Here's active publishers on climate change. And here's climatologists who are active publishers on climate change. So that's the sense of distance from the topic and level of belief. This is exactly what you would expect to see if we had an information crisis, if we had an information problem. If we needed to take information from the most knowledgeable scientists and spread it outward, it would probably go to the next categories of scientists out, and then eventually get into the scientists in general, and then eventually to the general public. And this is kind of where you go. One interesting thing is the I'm not sure, which tends to be very, very low for the climatologists, but kind of interestingly variable across the other populations. Okay, so here's an example of disinformation. This is not misinformation or uninformed like we just saw. This is disinformation. This little book is put out. It seems like something official. It's a second edition. We talked about a bunch of reports. Maybe this is one of them. Why scientists disagree about global warming? Do scientists disagree? Well, they've presumed that they do disagree, because why scientists disagree? That's what the title of the book is. This is the NIPCC report on scientific consensus. And the IPCC is a scientific consensus group body, so what the NIPCC must be related to that, right? This font looks an awful lot like an IPCC font. If I show you an IPCC book, you'll say, "How? Wow, it's very similar in the way it's laid out." This book has nothing to do with the IPCC. They did not win a Nobel Prize with Al Gore. The IPCC is a function of the United Nations, is a part of the United Nations through a series of IPCC bodies that guide of United Nations bodies that guide the IPCC and its sort of governance structure. They do work through climate change consensus. Everything in this book is about the agreement, not the disagreement. everything in this book is about the disagreement, not the agreement. Okay, so who does put out the NIPCC? It's actually, this is a publication by the Heartland Institute, which is a disinformation institute that puts out active counter arguments, but really kind of confusing topics about climate change. They are funded largely by oligarchs and oil companies, or fossil fuel companies. They printed many hundreds of thousands of this book and gave it to public school teachers all around the United States for free. It has lesson plans in it. It has homework problem sets. It has cherry-picked evidence. It has debunked cherry-picked evidence in it. It has a very short bibliography. This book has a very, which is what we've been talking about of this whole talk, it has a very long bibliography. Maybe that would give you pause, but there are summary documents from this book that look an awful lot like this book in length and in tone. This is an act of disinformation. This is producing something without really telling you why or who or what the purpose of that document is, or the rules by which it is used, and it is meant to confuse the audience. In those, not confuse them in what it is saying inside. What it's saying inside is that scientists disagree about global warming. That part is actually carries right through. They don't. We just saw the enormous agreement among scientists on global warming, but what it's hiding is its provenance. It's hiding who is behind this work, what they're doing, and why they are doing it. So if you are teaching this topic, you should teach from accurate sources. Here are some of the really good ones online that are free, but there are peer-reviewed journals, there are scientific societies, there are government and public funded research. These bodies have an agenda to at least be responsible to the paper trail of what they are publishing. They don't always get it right. They definitely do not. They have very contentious fights about tiny details. Sometimes they get derailed by those fights and prevent and things that should be published are not, things that shouldn't are. All that's part of the story, but at least their agenda is pushing towards getting the most accurate information out to the scientific world and the public as transparently as possible. And so this is a whole wide crew of folks who have been in on this. I'm not going to play this slide because I think it's going to kill the recording. But there's a diverse crew of scientists and engineers who have made contributions to the story of what is going on with climate change and what we will, what we take away from it. And I think it's, it's important to recognize everyone will suffer from climate change. Everyone can benefit from mitigation of climate change impacts, and everyone can play a role in developing that science or communicating that science back to their affinity groups. And their affinity groups need to be convinced as well, because this is going to be a hard thing to do. We all have to agree that it needs to be done together. So I have a couple of pieces about how I'll go about this. So you might say, well, can we do this all with just going after the fossil fuel industry? It's not enough of the economy. The fossil fuel industry, yes, it's supporting all these other pieces, but we have transportation issues. We have, we have housing issues. We can't just jump off of fossil fuels without replacements. How do we figure all those pieces out? So going after just one industry or just one corporation, who, even if they're a bad actor, it's a little bit like trying to lose weight by only eliminating desserts. It might help a little. It's probably not going to solve the problem all the way over. But we could think of climate wedges. This is a really nice paper from a group at Princeton, some authors at Princeton. And this, if we think of it compared to dieting, it's like we consistently make good choices. we make good choices at every opportunity. We have a no dessert, and we have a healthy salad, and we don't have too large of a portion, and we don't go out to eat very much, etc. We break down what needs to be done to go from increasing business as usual wedge, which is what they were thinking of, down to beginning to decrease wedge. And they said, let's just chop it up into these little pieces. And each of these little pieces will be the equivalent of about 1 billion tons of carbon per year by the end of this. And so they call that a fossil fuel wedge. And this kind of approach benefits from a quantitative appreciation. And in fact, this is very much what the Obama era plans were to satisfy the Paris Agreement Accords. So here is the New York Times illustration of that, very much inspired by this. Here is the business as usual forecast from 2016 when these pieces were put into place. I hate to tell you what happened in 2016, but anyway, here's the Clean Power Plan. That's a wedge. Here's changing fuel standards for personal and commercial vehicles, another wedge. Methane and nitrous oxide reductions, that the regulations to help that. Energy efficiency and hydrofluorocarbons, great. California, just their rules is enough to make a wedge. And we get close to the Paris goal, which is down here. So this is one way of going after the problem, that you put in bite-sized pieces, you add them all up, and when you get there, that gets you where you want to go. The problem with this is that every single one of these is a huge fight. Every single one of them can be reversed in court. Every single one of them might penalize one industry who's maybe not the biggest player in the game, but they just were easiest to regulate for political or social or cultural reasons. So an alternative is not to quibble about the details and address it all at once. And so this is called, at least by these folks, the conservative case for climate action. And the diet equivalent here is to count calories, which is you do it across the board on every single thing that produces carbon in the system. There are a lot of sort of tweaks to this. But really the point here that I'm trying to make is that how we reduce carbon, how we mitigate climate change isn't a scientific question. The scientific question is what happens when we emit a certain amount of carbon by a certain time. The political question is how we get movement to equitably and fairly take the carbon out of our economy, take the carbon out of our lifestyles, do it in a way that we can do it globally all together, get ourselves so that the cheaters are punished and the early adopters are rewarded. That's the kind of system we want. That's what we want. And the people who can't afford to make the change right now are either given support from other countries to make the change, or they're given a different pathway to making the changes that they can make. That's the kind of political action that's important for this extremely complicated problem, not what we normally think. The other thing we can do, of course, is we can do geoengineering. We can try and change the Earth system to make it easier. Some of these are pretty minor, like green roofing, change the albedo. Some of them are getting a little bit more major, changing the ecosystems. We can brighten clouds, change stratospheric hours. So there's an issue about whether these will do no harm. Some of these have very modest side effects, and lots of them have beneficial side effects. Some of them have really massive side effects. And this is the diet equivalent of taking a weight loss pill. What we cannot do about climate change is nothing. We have been ignoring the problem. We are now beginning to adapt. The consequences are here. We're getting all the fires, getting lots of warming pieces. All of that is coming. There's no way around the story. We're going into this now. We can try and mitigate the distant future changes, or even the relatively near future, the decades from now changes, by changing what we're doing now. But we're stuck on a trajectory that's going to have increasingly difficult problems for the next few decades to next few centuries as we figure out how to adapt to these problems. So the diet equivalent to adaptation is not a good one. You are talking about treating the diseases that come with obesity. So that's things like, getting kidney dialysis for your diabetes. That's not an ideal solution, but that's the pathway we've been on so far, largely. All right. So how to handle the climate change is part science, part technology, part politics. All of it requires a quantitative appreciation of the problem. Our business in this class and elsewhere is to really provide that quantitative science to make all of the science developments, all the technology developments, all the political developments really make sense so that we're actually solving the problem that is the problem, not doing things that look like the problem. What we can do is build our quantitative skills and capabilities, foster an appreciation for accurate, precise information. That's why I'm glad you all took this class. Thank you very much. We can discuss this on next week if you want, or not, but it's been nice having this time to talk to you all. I hope this last piece isn't too preachy. This is the reason, it's become increasingly the reason why I'm doing this work. I hope it's inspiring to you, whatever your path is from here. See ya.